My name is Marina, and today we are measuring time versus temperature. Our experimental setup consists of an iron, an infrared thermometer, and a timer. We use the infrared thermometer to measure the temperature of the iron, and the timer to time every 5 seconds. Our goal is to record the time it takes to reach the max temperature of the max setting of the iron.
My name is Colin McGee, and I'm going to be talking about the experiment instruments that we used for our time response experiment. First, we used an 1100 watt clothes iron that was powered by 120 volts and weighed 1 kilogram. In order to measure the temperature, we used a Fluke infrared thermometer. The model was a 62 Max Plus. It has a range of negative 22 degrees Fahrenheit to 1,202 degrees Fahrenheit, and it has an accuracy of plus minus 1.8 degrees Fahrenheit, or 1% of the reading, whichever is greater.
Alright, I'm McGee Shettlesworth, and now we're going to create our mathematical model of the data that we recorded for the iron heating up. We start with a second order differential equation where big T is temperature, which is a function of time, and we have three constants in our equation, C, K, and A. C and K can be thought of as being analogous to a spring mass damper system, where when you change the C value to be higher, it decreases the time response slope, while a higher K value will increase the frequency of oscillations in the solution. Also, we have the initial conditions. 74 degrees is the temperature of the iron at time equals 0. T dot of 0 is equal to 0. In order to get our transfer function, we take the Laplace transforms of the differential equation above, and after distributing this solution, we have this form right here, which is now ready to be plotted in MATLAB. So in MATLAB, we use ODE45 and the impulse function to plot our solution, as well as we typed in all our data collected from measuring the temperature at different time increments. And let's look at our plots that we generated, and you can see that we have, and shown as circles is our data that we recorded. And you can see our max temperature is about 435 degrees Fahrenheit, and time response is about 49 seconds. And this actually ends up being about 8.78 degrees Fahrenheit per second for the rate of time response. And you can see also that our ODE45 and the impulse plot are lined up on each other. And the way we got it to get about as close as possible to our data plot was playing with the values of C, K, and A. So we basically did a guess and check of these variables until we got something that resembled what we actually recorded. And we notice that it reaches its max temp, and then it drops down to about 360 degrees and goes back up to 390 degrees. So it looks like it hits that peak of 435 degrees Fahrenheit, and then it'll begin to oscillate between 360 and 390 degrees Fahrenheit. Now you can also see that our data ends at about 130 seconds, and that's why we have this cutoff right here. And that's it.
Alright, this is our infrared thermometer. This is our iron. To start, we took the temperature of the iron at ambient temperature before we plugged it in. And in order to start the operation, we then plugged in the iron and started recording data points. And as you can see over here, we have the display of the temperature of the ambient temperature of our iron.